Welcome back to the lectures in chemistry and on the atomic structure and chemical bonding. This is the second part of the video tutorial which was discussed in the previous lecture. The video tutorial is on the problems and solutions in Hermite polynomials and in hydrogen atom. And let me recall that there were 9 problems in the tutorial that I have circulated to the course and in the course, and this is the point where we stopped in the previous exercise. Okay. So, this problem is to verify that the 1s and 2s orbitals which have been given to you through the lecture notes and also through the lecture are eigenfunctions of the hydrogen atom Hamiltonian, and it asks you to obtain the eigenvalues explicitly. Let us go to a fresh page. The hydrogen atom Hamiltonian, the wave function for the 1s orbital is a normalization constant times an exponential minus r by a naught. A naught is the Bohr radius. And the solution is h psi 1s is equal to E1 psi 1s, where E1 is the ground state energy. Now, the expression for the ground state energy is the same as what Niels Bohr had given, and we should keep that in mind, as well as the expression for A naught. Recall that A naught, the Bohr radius, is given by the following form. If you recall the hydrogen atom Hamiltonian as minus h bar square by 2m 1 by r square d by dr r square d radial part. So, let me write to this as psi 1s trans psi 1s dr. The other is the angular part, which acting on the radial function gives you 0. Therefore, we do not need the component, but then the potential energy expression is minus E square by 4 pi epsilon naught r times the radial function. This is what we have to show as E1 times psi 1s, psi 1s being the radial function here. Now, recall that A naught is from the Bohr's theory, and it is still valid. It is a definition for the Bohr radius, epsilon naught h square by pi mass of the electron, the charge square. Okay. So, let me highlight this. This is one expression we should remember, and the other one is the expression for the E1, which is minus the mass of the electron times the charge raised to the power 4 divided by 8 epsilon square h square, the Planck's constant. These two will come out from the Hamiltonian when we apply the differential operator. Okay, first 1 by r square d by dr r square d by dr of exponential minus r by a naught. If you look at that, it is 1 by r square d by dr minus r square by a naught exponential minus r by a naught, okay, which is minus 2 pi r e to the minus r by a naught times a naught plus r square will cancel out. You have 1 by a naught square e to the minus r by a naught. Okay. Hamiltonian is of course minus h bar square by 2 me times all of this, all of these. Therefore, what you have is you have minus h bar square by 2 me. Sorry, the Hamiltonian also has the potential term minus e square by 4 pi epsilon naught or e to the minus r by a naught. Okay. And if we substitute that in, we have minus h square by 8 pi squared me times minus 2 by r plus r a naught plus 1 by a naught square exponential minus r by a naught minus e square by 4 pi epsilon naught or e to the minus r by a naught. Okay. Substitute for a naught in this expression, you will see that this is exactly, this is positive and this is exactly the same as this term except for the sign. Therefore, this term can be cancelled to this term with this term. What is left over? You have to substitute for a naught using the expression for a naught given here, epsilon h square by pi me e square. Okay. You will see that these two terms cancel out. So, what is left over would be minus h square by 8 pi square me times 1 by a naught square, and a naught square, 1 by a naught square is pi square me whole square e raised to 4 divided by epsilon square h raised to 4 times e to the minus r by a naught. Okay. So, you can cancel off common terms. So, what you will get is, after cancelling all the terms, you will get minus me, there is an me here, there is an e raised to 4 here, and there is an 8 epsilon square, epsilon naught square, and a h square, and that is exactly E1, okay, times gives you minus E1 times e to the minus r by a naught. Okay. Here also the reason e to the minus r by a naught multiplied. So, psi 1s gives you the energy H1s is equal to minus E1. Okay. There is a minus sign, of course, because this is a ground state energy E1 psi 1s. Okay. Or if you write it as E1, you simply write this as E1, and E1 contains, I think this is consistent to what we had done earlier, but E1 itself is this expression with the minus sign. Right? Exactly the same thing can be done for psi 2s. The E2 that you should get should be minus me e raised to 4 by epsilon 8 epsilon naught square h square times 1 by 4. This is what you should get if you use the psi 2s orbital and do the differentials as indicated in the problem here. Okay. The next problem is on again some of the aspects of the radial functions. The first part is to obtain the most probable radius for the 1s orbital, and also do the same calculation for the 2s orbital. The second part to the problem is the value, the average value for the radius for the 1s electron orbital. And the third part is, of course, to get the square of the radius, the average value for that, for the 1s electron. We do 1s electron because it's a simplest radial function, but the calculations involving 2s and 3s or all the others is exactly the same as the calculations done for 1s. And the last is, of course, to give you an idea how to normalize an angular part by taking into account the non-zero angular part in a 2p orbital and obtain the normalization constant. So let's do one by one. First is the most probable radius for psi 1s orbital. This is problem 7. Most probable radius for psi 1s. What it means is that the radial distribution is r square radial function square. There is also a radial, there is a numerical constant, but we will not worry so much about that. So the most probable radius is to find out the maximum value, namely d by dr of r square, set it equal to 0, which gives you either a maximum or a minimum. It gives you an extremum, and then from the value of that r, calculate the second derivative of the same function and find out for which of these this is negative. That value of r is the one for which we have the most probable radius. Okay. So the derivative is very simple, d by dr, leaving out the numerical constant or the normalization constant. It is r square e to the minus 2r by a naught, because it's a square of the radial function, and that's given as 2r e to the minus 2r by a naught minus r 2r square by a naught e to the minus 2r by a naught, that's equal to 0. Since the exponential is never 0 except for infinite value of r, what you have is r into 1 minus r by a naught, that's equal to 0, which gives you r is equal to a naught, which is the Bohr radius. The most probable r for 1s orbital is the Bohr radius a naught. Talks about the insight that Niels Bohr had 15-20 years before all these things happened, and it's also an extremely important constant in the quantum chemistry and the all of atomic physics, a naught. Second problem, if I look at it, is the average value for the radius for the 1s electron orbital. So we need to calculate the average value for the expectation value r. You recall the average value a for any quantum system in the quantum state psi is given by psi star a psi d tau, provided psi is normalized. It's 1. Therefore, here we will use the normalized 1s orbital, which is 1 by square root of pi a naught cube exponential minus r by a naught. Remember, the normalization here is done using angular coordinates also. The pi is clearly there. So, what is meant by the psi s? Normalization 1 s, psi star 1 s, r square dr sin theta d theta d phi between the three integrals r equal to 0 to infinity, theta is equal to 0 to pi, and phi is equal to 0 to 2 pi. This is 1, and this is what gives you that constant 1 by square root of pi a naught cube. Therefore, when you calculate the average value r, you have to do exactly the same thing, namely r is equal to 0 to infinity r square dr and exponential minus r by a naught or exponential minus r by a naught. So, this is psi a psi, can write it as psi star. So, if this is the operator a, okay, and then of course, there is no other angular part. So, the angular integral will give you anyway 4 pi. Okay. So, what you are calculating is essentially 4 by a naught cube, cancelling off the pi's, the integral 0 to infinity r cube e to the minus 2r by a naught dr. Recall, simple standard integral e to the minus a r raised to n dr 0 to infinity. The standard integral is n factorial divided by a raised to n plus 1, where n is an integer, n is a positive integer. Therefore, we can easily see that the integral gives you 4 by a naught cube into n is 3, therefore, it is 3 factorial is 6, and the other is a naught by the constant a is 2 by a naught, and it is in the denominator. Therefore, you have divided by 2 raised to 4 a naught raised to 4, which gives you 3 by 2 a naught. This is the average value for the radius, okay, in the 1s orbital. Likewise, the average value for the radius in the 2s orbital, 3s orbital, etc., they will all be larger than this, and you can see that they correspond roughly to what Niels Bohr had a picture as an orbit of the electron, and therefore, the classical or the semi or the pre-quantum description that Niels Bohr gave using quantization of angular momentum on an ad hoc basis and using classical mechanics to get approximate values for the orbits, the Schrodinger's wave equation provides a mathematically clear and as we know today, the correct picture using the wave functions and the probabilities. Okay. Third, problem C is, if I recall, the average value for the square of the radius r square. Of course, the integral is extremely simple and straightforward. So, all you have to do is, again, for the 1s electron, it is 1 by pi a naught cube 0 to infinity for r square. Therefore, you have to write r raised to 4 e to the minus 2 r by a naught dr times 4 pi. This 4 is because you have r square dr as part of the integral, the element, the radial element. Therefore, this is also fairly straightforward. You can write this as 4 by a naught cube into 4 factorial, which is 24, divided by 2 raised to 5 a naught raised to 5, which gives you 3 a naught square. So, these are simple calculations involving the radial quantities, and now let us do a little bit using the radial and the angular quantities in the next problem. Namely, let us normalize the 2p orbital, or I think the orbital is r e raised to minus r by 2 a naught cos theta. Yeah, cos theta. So, the normalization now involves the angular integration also. So, if we call this psi as 2p as n or e to the minus r by 2 a naught cos theta, then the integral psi 2p square r square dr sin theta d theta d phi, the corresponding integration with the limits. If you do that, it is r equal to 0 to infinity r square, and there is also an r square here. Therefore, this will be r raised to the 4 power 4 e raised to minus r by a naught, the square of this function dr, that is the radial integral, and the corresponding angular integral is 0, theta is equal to 0 to pi. You have cos square theta, and then you have sin theta d theta, and then you have the d phi 0 to pi, which will give you 2 pi. Okay. Therefore, the integral is pretty straightforward. We have already done this integral earlier, integral cos square theta sin theta d theta, either in the problem or as a lecture note, and this you know is 4 by 3. Therefore, you can calculate this integral very quickly using the general formula for the exponential. You will get n square times 32 pi a naught raised to 5 is equal to 1, which will give you the constant n is equal to, so there is an n square here, yes. So, this will give you n is equal to 1 by 4 square root of 2 pi a naught 5. The normalization constant involves a naught raised to the power 5. That is important to recall, because you remember the wave function has the radius and therefore length coordinate, and the integral contain r square dr. Therefore, the wave function square will contain the length square, and the r square dr will contain a length cube. Therefore, the whole integral will have the dimension of length raised to 5 unless you have a normalization constant which takes the length raised to 5 and cancels it, in order to make this integral a probability and therefore a dimensionless number equal to 1. Therefore, you see this is clearly to be checked every time you look at the radial function. If you do a 3s orbital, you will see that the radial part is r square essentially. So, it means that if you take the square of the function, it is r raised to 4, and then the r square dr will also give you 3 more length cube. So, the wave function for psi 3p should have in the denominator square root of a raised to 7 and so on. I think dimensions are very important. So, these problems are not only to do the algebra, but to check consistencies in your results between the starting point and the end point. Okay. Therefore, the normalization constant for this function can be easily obtained by doing the angular integral. But of course, we have some more in the next 2 problems. Okay. Let us go to the next problem. It says from Wikipedia, write down the forms for spherical harmonics for all m values for L equal to 4 and L equal to 5. I use that source because I found that particular table to be very useful for my classes, and the table goes on for larger values of L equal to 7, 8 and so on. And you also have to write down the possible nodes for each wave function. Recall that an angular function represented by y, L, m, where L is the angular quantum number and m is the projection quantum number. the angular function has L angular nodes. Therefore, if you are writing the YLM for L equal to 4, every one of those functions will have 4 angular nodes. Every one of the functions YLM with L equal to 5 will have 5 angular nodes. So, let me just give you the table which I have copied from, and then discuss the angular nodes using that table. You can also get this from the internet. Okay. So, in this screen you see the angular functions for L equal to 4. There are 9 functions: y plus minus 4, m equal to plus minus 4, m equal to plus minus 3, plus minus 2, plus minus 1 and 0. First thing, when you see m equal to plus minus 4, the exponentials, you can see that they all take the m value. This is the m value, plus minus 3, plus minus 3, plus minus 2, plus minus 2, plus minus 1 e to the plus minus I5, and the m equal to 0 is, of course, this is 1. Second thing is, when L m, if m is odd, you will also see that between the plus m and the minus m, there is a sign change here. These are all standard throughout the spherical harmonics. These patterns are there. And the other important thing is that every function in theta is a homogeneous 4th order polynomial. For example, sin raised to 4 theta, no problem. This is sin cube theta cos theta. So, the homogeneous order 4 in sin and cos theta. Now, this looks like it is not, there is a minus 1, but I have told you this earlier, that minus 1 is nothing other than sin square theta plus cos square theta with the minus sign, minus 1. Therefore, you can see that this is 6 cos square theta minus sin square theta multiplied by sin square theta. It is homogeneous in order 4 with power 4. And likewise 3 cos theta, you multiply this by cos square theta plus sin square theta, you will also get that this is a 4th order polynomial, and likewise the 4th order homogeneous polynomial here by having this and this both multiplied by the unity. Okay. It's just, I mean, this is to tell you that there are patterns. Now, what about the nodes for these functions? The first one, let us take the function exponential y44 proportional to exponential I 4 pi 4 phi sin 4 theta. Theta is between 0 and pi. Sin theta does not go to 0, therefore, no angular node is due to theta, but exponential I 4 phi for the value of phi is equal to 0 to 2 pi has nodes in the following. Please remember, when we plot the cos and sine, there are 4 nodes. If we take the cosine 4 phi sin 4 theta, the real part will have at cos pi by 2 and cos 3 pi by 2 or the 2 places 2 values of theta for which the function is 0, but cos pi by 2 is the same line as cos 3 pi by 2. Therefore, we do not have that, it is only one node, and now it is 4 phi. Therefore, we have phi is equal to pi by 8 in the circle. If we have to write, this is the phi, okay. At phi is equal to pi by 8, 3 pi by 8, this is 5 pi by 8 and this is 7 pi by 8. Of course, this axis extends here, this axis extends here, therefore, this is all the angular nodes. So, all you need is only the 4 angular nodes, the first 4, this one, this one, this one and this one. This is not a node. Okay, this is just a 90-degree axis. So the last node that we have is 7 pi by 8. 4 phi is 7 pi by 2. All the odd integral pi by 2 up to this point. The other nodes are the same as these nodes, that therefore there are only 4 values of the angle. Okay. This is for sine cube theta cos 4 phi, and exactly the same thing that you can do for sine cube theta sine 4 phi, which is 0, the real part is 0 for the values 0 and pi. Between 0 and pi there are 4 values of sine 4 phi which would be 0. Okay. So, those are the 4 nodes. What about the nodes for, again one more example I will do, the example of sine square theta 7 cos square theta minus 1 e to the plus 2 I phi. This is y 4 2. Okay. Now, 7 cos square theta minus 1 goes to 0 when cos theta is plus or minus 1 by root 7. Therefore, those are the angular nodes in the radial coordinate theta 0 to pi. So, the values of plus minus 1 by root 7. So, somewhere here and the corresponding minus. Okay. 2 nodes. These are the nodes due to the theta. The nodes due to the value of phi are cos 2 phi and sine 2 phi, one of them. Cos 2 phi has an angular node between 0 and pi at 2 phi is equal to pi by 2 or phi is equal to pi by 4. Exponential 2i phi corresponds to that phi distribution. Therefore, there are 4 lobes and phi is equal to pi by 4 and phi is equal to 3 pi by 4 are the 2 values for which the real and the imaginary parts, the real part goes to 0 and then the imaginary part goes to 0 for corresponding other values. So, those are the 4 angular nodes with respect to the y, L equal to 4 and m equal to 2. So, likewise you can calculate all the other angular nodes for the problem. Okay. The last problem is, of course, I have not said anything about L equal to 5 in this problem. Exactly what has been done, I have grouped them into 5 categories of functions: plus minus 4, plus minus 3, plus minus 2, plus minus 1 and 0. In the case of L equal to 5, you will have 6 of these, and you can see again 5, 4, 3, 2, 1, 0, 6 functions. Totally there are 11 spherical harmonic functions, and they will be grouped into the pattern with which I explained L equal to 4. So, you can do that yourself. Now, the last problem is to practice integration by normalization of some of the angular functions 2p, 3d and 4s. So, I shall indicate simple steps, and I think the algebra is something that you can do yourself. Let us do 3d, the angular part of 3d, easy enough. This is problem 9. Okay. Angular part of 3d is 3 cos square theta minus 1. Okay. Remember, the psi 3d contains a radial part with the n equal to 3 and L equal to 2, and the L equal to 2 and m. There are 5 of these, m equal to 0, plus minus 1, plus minus 2. Therefore, the normalization essentially means psi 3d square absolute square. I think that is important now, because the functions can be complex. Then you have r square dr, then you have sin theta d theta and d phi. So, if you take the absolute square, the exponential parts go away. So, it becomes 2 pi, the m disappears, and what is left over is the spherical harmonics y 4 m theta phi square 0 to pi sin theta d theta, which can be separately normalized, and the other being the radial function or n L, n is 3, yes, n is 3, L is 2, radial part r square, and you have r square dr between 0 and infinity. This can be separately normalized as a radial function, and we will just concentrate on one of this corresponding to y 2, sorry, this is not 4, this is 2, y 2 0 theta phi, which is 3 cos square theta minus 1. Okay. Therefore, the integral y 2 0 square sin theta d theta is the integral 0 to pi 3 cos square theta minus 1 whole square sin theta d theta. You can easily do the change of variables, cos theta is equal to x, and follow up all those things. So, you will get from minus 1 to plus 1 dx, you get 3 x square minus 1 whole square. Simple enough integral, and I would let you finish that by yourself. 9x raised to 4 minus 6x squared plus 1 dx between the limits minus 1 to plus 1. Okay. Please do this. But all of the algebra that I have mentioned in the video tutorial is only to give you a feeling that you can do the algebra yourself if you spend sufficient amount of time to sit down and learn. What's the purpose? The purpose is, of course, to make you more comfortable with the whole mathematical framework, however elementary it may be, with the chemistry, the quantum chemistry part of it. But even more importantly, all these things are the basis and the idea of the linear combination of atomic orbitals, etc., are based on our understanding of the hydrogen atom orbitals and the way that the electronic structure, an approximate electronic structure of the atom, is organized by the principle of the Hund's maximum multiplicity, involves this fundamental idea of the hydrogen atomic orbitals. Therefore, familiarity as well as a fairly complete understanding of the hydrogen atom problem in quantum chemistry is fundamental to understanding all of quantum chemistry. Okay. That's the reason why this tutorial has so many algebraic calculations. I have not given any numerical results in this particular tutorial. Many of that can be found in several textbooks. Okay. We will continue with the lectures in the next set, and we'll find out about the general principle of the linear combination of atomic orbitals and others in the succeeding lectures. Until then, thank you very much.